Hello and welcome back to Data Science Castnet. In today's video, I thought I'd show you this idea that I've had kicking around for ages, but that resurfaced recently and got implemented. And it's a thing, I call them kernel crystals because you get some sort of crystallized like shapes, but the core idea, I guess, officially would be something like a multi-scale convolutional cellular automata or neural cellular automata, but with randomly initialized weights. So these are not learned systems. They're just creating a random kernel, but you get these beautiful patterns out, often very, very like intricate and fun. So in this video, I thought I'd go through a bit of the backstory and inspiration, I guess, for why this idea was knocking around in my head, how I explored like initial implementations myself, tinkering around, and then finally how I created this beautiful WebGL-based site where you can, mess around with what if we started with a radial gradient and we started at 8 by 8 pixel resolution? What would that look like as that update is repeatedly applied? Okay, so let's talk, I guess, how this works, and then about the backstory. So the idea here is actually pretty simple. We're going to represent some grid, right? And this is going to be our image. And I'll draw this as a single channel image just for simplicity, but we can do the same thing for multiple channels. All right, so each of these values here has some initial, color, right? Some darkness, some might be dark, some might be light. And the idea is we want to compute an update. Like if I'm looking at this location here, we're going to compute an update by looking at the surrounding 3 by 3 neighborhood and applying a 3 by 3 kernel, right? So just a 3 by 3 matrix of numbers, right? 1, 0, 0, 0, 0, 0, 0, 0, 0, for example. This would say take whatever value is in the top left corner and multiply it by this, and then add whatever values here, multiply by that, and so on and so forth for all 9 values in the kernel block. And that's going to give you a final output. And then we're going to multiply that by some update factor, some delta, right? Some scaling. And we're going to add it to whatever the initial value is there. And we're going to do this for either for all locations or, more interestingly, for a subset of locations, right? So we apply our kernel randomly to, say, 50% of the total number of pixels in our grid. So this gives us a so-called convolutional cellular automata. And to show, this is another inspiration for that. Back in the day, I remember this neural pattern site that let you randomly create a kernel and a filter that could create some somewhat interesting patterns already. And that's covered really well in this What Are Neural Cellular Automata video by Emergent Garden. So I'll definitely link those down below to explore. The thing that makes the kernel crystals fun is that it doesn't just apply this at a single scale. So what we're going to do is we're going to start with some fairly small grid, and then we're going to apply some number of steps, and then we're going to change the resolution, right? So every pixel here is now going to get divided into 4 much smaller pixels, and then we're going to apply our same rule, but now instead of applying over this large area here, after a resize, we might only be applying over some much smaller area here. So you get this multi-scale detail out, these multi-resolution patterns, and that, in my opinion, leads to some of these really beautiful and interesting different emergent pretty patterns. Anyway, so yeah, that's the core idea. Some other inspirations. So one early one was this idea of neural cellular automata, including the idea of randomly applying the updates to some subset of grid locations rather than to all of them. That's from this DistalPub publication from 2020 by Alexander Mordvintsev and co. Michael Levin, some of you may know from his work in biology. And so this was a very, very inspirational paper for me, very pivotal. Likewise, they did a follow-up that did generating different textures with learned neural cellular automata. And so I got really into that back in the day, set up a system that did these neural cellular automata, but where you could use clip to give like a text description as well as an image. So here was like glowing dragon scales, I think the prompt was. And then instead of like that random 3 by 3 kernel that I've been showing for the kernel crystals, we instead have some learned set of weights, right? A learned larger set of numbers that are sampled for the 3 by 3 grids around some particular coordinate, and then that gives you a sort of more complicated update rather than just the applying the kernel. And then even back then, so this was what 2022, I think I wrote this up, but yeah, a lot of this was done earlier in 2021. I did the same thing of like this kind of fractal zooming where you'd apply the learned cellular automata in this case at one resolution and then again at a different resolution, again at a different resolution. You get these beautiful sort of fractal crystally images. Anyway, so yeah, super cool back then using these learned weights, but I thought it never did occur to me back then to attempt this multi-scale thing with randomly initialized weights. And so, yeah, more recently, like I woke up with this idea and some very quick back and forth in a little exploratory. This is Solve It. It's kind of like a dialogue notebook thing where you can, get the AI to write the boring bits and explore back and forth and create these visualizations. Okay, what if I start with a seed crystal? This is just single channel, applying some kernel some number of times, slowly building up to like, okay, what if we did this for 3 channels? What if we did this, at multiple resolutions? And yeah, explored with different, like, how many steps do you do at each scale, and what percentage of the image do you update each time? How much do you multiply the kernel's final output by when you're doing the delta? Are you clamping, etc., etc. So very fun to just like kind of play around. And then this website is just literally the sort of, okay, I would like to turn this into something everyone can play with. I know WebGL has the mechanics for very rapidly applying this kind of computation across an image or a pixel buffer. So I just used Codex to take that exploratory notebook that I'd done with all of my sort of waffling and ranting and exploring of different settings, and then convert that into, some more interactive and pretty looking website that you can all try. So this is available. I don't know if OBS will show the URL. It won't, but I'll make sure to link it in the description. Anyway, but I thought it deserved a bit of backstory rather than just like, hey, click the button and get pretty pictures. Now you know what's going on. There's this idea of a random kernel. And in fact, if you go in the browser, if you open up your console, you'll see for each one, you can see the configuration, which is the kernel itself, right? 81 values being 3 by 3 for the per channel. And then there's 3 channels, so 3 by 3 by 3 by 3, right? Because you want RGB in and out in that local neighborhood. And then the base size, the number of steps up, the number of steps. In this case, I kind of let you do fewer steps at the beginning and more steps at the end. But you can also tweak that to say, okay, just always do 20 steps. And if you put this number low, like 10, you can see a lot more artifacts of like the early, I guess start at 16 pixels. You can see the kind of like multi-grid artifacts there. Very, very satisfying to play with. Yeah, anyway, so go have an explore, mess around, share any cool kernel crystals that you find with me. I would love to see that. And yeah, it is a particularly entertaining way to get some pretty pictures out of randomness. And of course, I'm planning to then search through this in various automated and human ways. I think it'd be fun to do some kind of pick breeder style evolution of the different kernels, see if we can find some particularly fun sets of parameters. Anyway, a lot of waffle. Thank you so much for watching. We'll see you in the next one.